Bienvenido al video 3.7.4. I don't know how to say derivatives. My Spanish doesn't get me that far. All right. It's 374, Jason. Or 373. All fixed. So let's start with an example. Let's actually use the inverse function theorem for something useful. Shall we? Find the derivative of the following functions. Part A, I'm still in green. Wow. Feeling very Grinchy. Actually, I identify a little bit with the Grinch. G of x equals inverse sine of x. This is not an easy thing to take the derivative of. This is not a nice function. The domain is wacky. The behavior is wacky. Let's remember what inverse sine is, shall we? So inverse sine of x, also known as arcsine of x, looks like this. It's a very small little function. The inputs only go from -1 to 1. And the outputs go from -π/2 to +π/2. So right off the bat, we're getting close to a vertical tangent line. So the slope is going to have to get close to infinity here. Slope is going to get close to infinity here. And our slope function, our derivative, is only going to be between -1 and 1. And it won't include -1 and 1 as well, because the derivative is a limit, and limits need to exist from both sides. But at this point, first off, the slope is approaching infinity. Second off, there is no slope from the right. There is no function from the right. That already tells us a little bit about what our derivative is going to look like. So let's use the inverse function theorem. Let's call this f inverse of x. And let's say f of x is sine of x. Now, we need to be a little careful again with the domain. We're only looking on the interval from -1 to 1. And specifically, we're really only looking at the open interval from -1 to 1. You could start with the closed interval, and you can see. Let's actually start with the closed interval, because that's all we know. We know the domain of inverse sine is from -1 to 1, and we showed that graphically as well. And then we'll show with another reason why we have to make it an open interval instead of a closed interval. All right, so inverse function theorem says that the derivative, g prime of x, is going to be 1 divided by f prime of f inverse of x. So again, we just go in order. What is f inverse of x? Well, we're saying f inverse of x is just g. It's sine inverse. All we have to do is plug that in f prime and we're going to be done. It's not that bad. Much better than the rational function we did in the first video. Well, what is f prime? F prime of x is cosine of x. Okay, that's not bad at all. So we just need to plug this into cosine. We get 1 over f prime is cosine. But instead of plugging in x, we're plugging in this whole thing. Remember your function composition. Inverse sine of x. And you might say, Jason, this kind of sucks. This is not a nice function. Don't circle this, because this is not our final answer. Undo. If you have a pen, I'm sorry. I tried to warn you. We can simplify this. Remember back to your pre-calc 2, your trigonometry. You remember simplifying the cosine of inverse sine of x? X is some number between -1 and 1. How we did it, we'd say, well, this is some angle, right? Sine inverse takes in a ratio and spits out an angle, whereas cosine takes in an angle and spits out a ratio. Okay, I can feel your energy. It's not even at the same time, but I can feel the energy of you guys when you're seeing this. Remember your trig. It's not too bad. Let's look at something. What do we know about this theta? Let's try to get a picture. Well, if theta is inverse sine of x, The whole idea about inverse sine is that means that sine of theta is equal to x. Sine inverse of a ratio equals an angle is the same as sine of that angle equaling a ratio. This isn't written as a ratio, so let's make it one. Opposite over a hypotenuse, x over 1. So if we draw a triangle, and again, it's either in the first quadrant or it's in the third quadrant, right? If x is positive, opposite over hypotenuse, it looks like this. If x is negative, it looks like this. It won't end up mattering since we're only looking at the cosine of that angle. And cosine is the same in the first and the fourth quadrant. There's both positive in both quadrants. So it won't actually matter. So what's the cosine of that angle? Well, that's adjacent over hypotenuse. We have a right triangle. We don't know the adjacent, whatever this is. We can use the Pythagorean theorem to get it. So again, I want to have everything on the same page, but it would be best if you wrote this somewhere where you had room, but I don't want to switch pages for all of you yet. Again, let's call this a or whatever. A squared plus x squared has to equal 1 squared, Pythagorean theorem. We want to solve for a. A squared is equal to 1 minus x squared, or a is plus or minus 1 minus x squared. But again, we know that it has to be positive here. Why do we know that it has to be positive? We do know it has to be positive here. A value has to be positive. We know we're either in the first or the fourth quadrants. Because... oh no, I'm forgetting. I can cover it later. Let me know if you have questions. But I don't want to delay the video. So cosine is that a adjacent over the hypotenuse, which is 1 here. Okay. Oh gosh, that's going to bug me. So that is cosine of theta. That's exactly what we wanted, right? This is cosine of theta. So this denominator is that. So g prime of x is just the reciprocal of this yellow circle, which is 1 over square root of 1 minus x squared. That's the derivative of inverse sine. So it's kind of weird. The derivative of inverse sine actually has nothing to do with trig, right? It doesn't look like it has anything to do with trig. It actually does have something to do with trig. This bottom thing, you look at it's a little secret. It's a little secret relationship with trig. If you look at the bottom thing, what is that bottom thing? The square root of 1 minus x squared. And let's make our, let's stop stretching it. We don't stretch it anymore. Oh, it's still stretched because of, dang it. There we go. Now our squares are actually squares. The denominator is the equation of a semicircle. So semicircles, circles. Trig is all about circles and triangles, right? Unit circles, reference triangles. Some good stuff. All right, let's use this result to do parts B and C. Find the derivative of this function. This is a different g of x, different problem. So it's not the same g as before. So we're going to just use the chain rule. Right? The derivative of h is the derivative of the outside function, which is 1 minus something squared. Right? That's what the chain rule is. Derivative of the outside function. Leave the inside alone. So again, we replace the x with g. Take the derivative of the outside function, leave the inside alone, and multiply by the derivative of the inside function. We can clean this up a little bit to get g prime of x over the square root of 1 minus g squared. This is optional shorthand. You can leave it in this form if you'd like. That's all it wants you to do for part B. And part C is going to have us use this. So part C, again, this is the derivative of inverse sine of g of x. Part C wants you to find the derivative of h of x equals inverse sine of 2x cubed. You can either use that formula from above, or you can do it manually with the chain rule. I actually think it makes a little bit more sense to do it manually with the chain rule. And I want to show you that for practice. Bless me. Sorry about that. But yeah, you could do it either way. We'll use let's use the formula. We've got it. May as well use it. So the derivative of sine inverse of some function g, right? This is our g here, is going to be g prime, which is 6x squared, using the power rule, divided by the square root of 1 minus g squared. Well, what is g squared? 2x cubed squared. That's a monomial, so you have to square each part. That's 4x to the 6th. All right, and I'm pretty sure that's all you can do you can't simplify this any further, because you can't factor anything out of the bottom unless you did some weird substitutions, but we're not going to worry about those weird trig substitutions until calculus. And then we'll do some fun stuff with something like this. Wait, this is calculus. I meant calc 2. Integral calculus. Trig substitutions are a really fun way of taking integrals. Oh, that's one of my favorite parts. But we're not doing that yet. So we talked a little bit about inverse sine. We found inverse sine with the inverse function theorem. Well, you could do the exact same thing with all the other ones, but I'm not going to make you. You can reference this theorem 3.13, and I'm just going to give you the derivative of every single inverse trig function. We already covered this first one, right? The derivative of arc sine is 1 over the square root of 1 minus x squared. Well, cosine is kind of funny. Arc cosine, inverse cosine. We just copy the exact same formula and add a negative. Look at why that's the case. Let's look at the graph. Inverse sine and inverse cosine. Notice that these are basically the same graphs, just flipped and then shifted up. Just reflected and shifted up. So the slope at any point, like the y value doesn't matter. The slope at any point is going to be the same regardless of y value. If you wanted, like, you could just subtract pi over 2, and these are going to have the same slopes. You notice the slopes are just opposites of each other. Okay? Because if we shift it down, these two functions are just reflections of each other. All right. And it turns out that that's actually the case with every single trig function. Tangent and cotangent, same formula, just with a negative. Cosecant, secant, same formula. Guess which one has the negative? All of these derivatives, I think literally every derivative with a co in it has a negative. All right, so sine inverse and cosine inverse, these are like moderately common. Inverse tangent is the most common. This is the one that's going to pop up the most, especially in Calc 2. All right, it's a very common one. Let's classify them. This gets the red one. These are going to be blue. And then so again, what's the derivative of Arc cotangent. It follows the same pattern. It's just the negative. We actually almost never use this one. Let's make this a green one. Red is common. I don't know what this color coding is. Red is common, blue is medium, and green is uncommon for you to see. In this section, you'll see them all, but in future classes, red is the most common. Cosecant and secant are kind of weird. I literally had to write these ones down. I see them so rarely. They do pop up sometimes. It's cosecant, so it's going to have a minus. 1 over the absolute value of x times the square root of x squared minus 1. I really don't see this a lot. But it does exist. It does happen. So we're going to talk about it. And again, secant is just the same as cosecant, just without the negative. All right, so these, again, red is common. Blue is medium. Oops, I don't need to write blue. And the green are kind of rare to see. There's our shiny formulas for any Pokemon fans out there. Anyway, that's it. We'll do more practice of this in the next video.